Handles. Okay, so f prime graph is given. So y-axis represents slope. So these are all variations of positive slopes, negative slopes, and these are all positive slopes. So we can label accordingly here. Slope sign line, we can pick off all the x-intercepts. Whatever sits above is positive slope. Whatever sits below is negative slope. So don't look at the rise and fall, look at the location. Is it above or below the x-axis? So above, positive slope. All this is below, above, above. Concavity sign line, now you're looking for points of inflection off of the derivative graph, off the first derivative graph. So point of inflection, now you're seeking the peaks and valleys. These are where on the original graph, the maximum steepness is going to occur, and that's where point of inflections will live. So -1, 3, and 5. 5 is a duplicate. It serves both purposes. It's an x-intercept and it's a peak and valley. So that's why it's going to show up in both sidelines.
Wait, so is there no like -4 or 7? Because it has like it ends there. That's like the domain.
Oh. Oh yeah, you're right. Yeah, those are the endpoints.
Okay.
Yeah, so you're right. Yeah, so endpoints should show up on my sideline as well. Yeah. So again, -1, 3, and 5. And then to fill in your concavity information, now you can look at the slopes. So negative slope is going to indicate where the original graph is going to display concave down. Positive slope is where the original graph is concave up. Negative slope, positive slope.
Is it when this slope is positive or when it's increasing?
When the slope is positive, or when the graph is increasing, which means positive slope. Right. So if I'm pulling from the slope side, if I'm looking to fill in my slope sign line, then I'm just looking at location, looking to see is this graph above or below the x-axis.
Yeah.
But if I'm trying to fill in the concavity sign line, I'm looking at the slopes. So negative slope means the original graph is going to have a concave down shape.
Okay. So it's not necessarily when f prime of x, the y value is above 0. It's when it's.
That's right, when it's rising. Yeah.
Thank you.
Okay. And the reason why that's the case is because let's pick off, let's just do ballpark values, right? Maybe this is a slope of 3. Oh yeah, sorry, 2, then 1, then 0, then -1, right? 2, 1, 0, -1. If you think about what that looks like on the original graph, it'll look like this: 2, 1, 0, -1. right? Slope 2, slope 1, slope 0, slope -1. And that's why this information is going to end up looking like this on the original graph. Okay.
Thank you.
Mhm.
What package is that?
This is the new one that you picked up here, page 2,
Thank you.
and I have. And then if you have all this information filled out, then or if you have the sign line, then it's easier to figure out what all your because statements look like. So you're just reading off of your sign lines to fill that out. Use the space below to sketch the graph, since I didn't have that show up on this one here. So cross off number 5 and see if you can sketch the graph based off of your slope sign lines. And again, the location doesn't matter. We're just trying to get the graph to have this shape, and then update it with curvature, and also sketch your second derivative graph. See how that looks. I have, I'm going to highlight -1, 3, and 5 on my graph. And that's my target for where my concavity is going to change. So concave down, concave up, concave down, concave up.
Oh, we shouldn't highlight the endpoints.
That's fine, you can, but we don't know where those endpoints are. Yeah, that's fine if you want to. Yeah, we don't have to highlight the endpoints now, because the endpoint is not going to. It's not going to be any shift in curvature.
So we don't know if it's a concavity change or.
Yeah, we don't know, right? We don't know if it's concavity change. It doesn't really matter what happens at the end.
Thank you.
Starts below, then above, then below, then above.
So basically we do the rough sketch.
Yep,
So
based off of your first sign line. And then you're just going to plot these points wherever your graph lands, and then retrace your graph with more pronounced curvature. Yeah.
thank you.
Morning. Okay, flip a few pages over. Let's do an optimization problem here. Zana, I have handouts. Did you want to pick those up? Yeah, you pick up both. So this is yeah, near the last page of your packet. Oops. That's right. All right, the length of its base is twice its width. So you can call one side x, another side 2x. And the height has no relationship with with the bases, so it'll have to be on its own variable. Build your surface area formula. And then once you have your surface area formula built, then work in, fold in that cost information. And then we can update that surface area to the cost formula. Oops, sorry. Stuff 2xh. 2x. So the base is 2x squared. One of the sides is x times h. The other side is also x times h. The front is 2xh, and the back is also 2xh. Thanks. I'm doing a BC help session, but you can stay here and ask questions. I'm just going to be doing mainly BC. But if you want to come, if you're working on something, I can answer your questions.
Okay, it was kind of like a topic, so I can wait on it.
Okay.
Thank you.
Yeah. Okay. Are we comfortable with creating our surface area formula on our own? 5 sides are accounted for, or 5 surfaces are accounted for. I got the base, and I have my 4 vertical sides. Okay. And then you're going to multiply in your cost. The base is going to be the most expensive, and the sides will be a little cheaper. So now I can update this to call this the cost equation. So this adds up to be 4, 5, 6, 6xh times 6, 36xh. So ultimately, we're trying to find the derivative of cost because we're trying to cheapest container. So we're trying to optimize cost. But to optimize cost, we have to get this down to one variable, and that H is sticking out. So we're going to use this volume supporting equation to help us get our cost equation down to X, just X. So now if I can just get this down to something cleaned up so I can use power rule, then I can do derivative, set equal to 0, solve for X. And once I solve for X, then I'm just going back and seeing, what am I really looking for? And we're just plugging into whatever one of the formulas that we've already established to get our answer. So begin your cleanup process. All you need is power rule to find the derivative. I took that 10 over 2x squared and I reduced it to 5 over x squared, multiplied it out, get it ready. And this should be where I'm at before I begin my derivative process. C prime, power rule, set my derivative equal to 0, solve for x, get my decimal value. And then finally, I'm trying to find cost. So I'm just going and searching for a cost equation that I've already built. Any of these cost equations work, just make sure you don't put it into C prime. I'm going to just choose the one that I feel is either of these I think are relatively easy to plug in. So plug 1.651 in for the x's, and then that will get you your optimal cost.
So basically use the derivative of cost
To get your critical point.
to get the critical point, which is a relative minimum or maximum.
Exactly.
And then you just plug in that next value to the original cost expression.
Or one of the original equations. It depends if it's asking for cost. Sometimes it could be asking for the dimensions. If that's asking for the dimensions, then you'll just, you have x, so you can get to 2x, and then your h is already defined, so just plug it into one of the h equation.
Okay.
Yeah.
Thank you. How many different shapes will we have to do for optimization?
Just as the only shape.
And it's just basically it's all the same process except for the ends, depending on how you have to.
Exactly. Yeah. Yeah.
Thank you.
Yeah. Your problem will look just like this. You won't. It's not going to. Yeah. That would, yeah. I mean, if we're looking for maximum, it wouldn't be cost. If we're looking for maximum, it would have to be something like volume. Yeah. But the process is the same. If that's the case, then you're trying to get your volume equation down to one variable, derivative, set equal to 0.
Another way we can use the surface area and volume equation.
Exactly,
to find a variable and then
Mhm.
plug that into the other one.
exactly, yeah. But the problem that you're gonna see is most likely gonna be cost. Yeah. Looking for that optimal cost. Why don't we do a mean value theorem and extreme value theorem? Um, yeah, it's not included in this packet. Let me, if you guys get a sheet of paper, I'll write it down. It's- So remember the process for extreme value theorem. First, establish continuity. Second, find critical points from f prime. Consider whether any of your critical points are valid. Are they all inside the interval? If they are, then you're going to test your endpoint and critical point back into the original function, and then finally compare the y values. Okay, do you guys find your critical points? Okay. Are both of these valid? Yes. So we're going to test all 4 points back into the original function. Use your calculator. Okay, good with one. All right, number two, we have g of x, determine if mean value theorem applies. And we want to make sure we state our conditions, right? We have two conditions for mean value theorem and roles, continuity and differentiability. So practice writing those statements out. And then after that, you're just making sure you're going through your process. So again, the formula is find the slope between the endpoints, get that number first, then find the derivative, and then set them equal to each other and try to solve for x. Ultimately, we're looking to first establish what is the slope between the two endpoints. And then we're asking the derivative to tell us where the curve is going to experience that exact slope that we found.
Do we have to write out g of 2 equals 2 cubed?
You have to
Like doing.
no. If you don't show your work, it's fine. You can use your calculator, get those endpoints, get your slope. I don't mind. You'd have to show your work too, how you got those values.
Thank you.
But just be aware that a common mistake that students make is they find the derivative first and they plug the negative 1 and 2 into the derivative, and then then they're doing f prime of b minus f prime of a or b minus a, and that's the wrong process. So I really encourage students to do this first. That way you're not involving that derivative function in the wrong process, in the wrong way. Yeah, good point. Yeah. Your for mean value theorem, our C value cannot live at the endpoints. It has to be between. Yeah, so this is a good example to see, oh, -1 looks like it could fit, but it doesn't fit. For extreme value theorem, we do include endpoints, but not for mean value theorem. Yeah, this is good good instance of that kind of subtle process for mean value theorem.
So we should only ever find one c value.
You may get multiple ones, but they all have to live inside the interval. Yeah, but you're guaranteed at least one. If you don't find any, then something didn't go quite right in your algebraic steps. Thank you. But yeah, usually if you get more than one, we're really, careful about that second one. We really want to make sure, is that second one going to pass? Because a lot of times it doesn't.
There's a problem where we're asked to find a relative extrema of an interval. Would it be the same process as EDT, but you just don't include endpoints?
If you're trying to find relative extrema, then it's just first derivative test. You're just finding f prime, critical points, plot your sign line, and then look for relative max, relative min. You don't care about the other points, right? Yeah.
Thank you.
Rolle's theorem is very much the same process as this. The only difference of the Rolle's theorem is that when you find your slope between the endpoints, it has to be 0. If it's not 0, then it's good for mean value theorem, but it's not good for Rolle. So this has to be 0. If that slope is not 0, then we can't guarantee the slope 0.
That's the only distinction with Rolle's theorem. But it's the exact same process, same conditions, same way to look for your C value.
If we don't use Rolle's theorem, we can find the same answer.
Right. But the only way that you have to worry about Rolle's theorem is if they actually state it. You have to say, determine if Rolle's theorem applies. Then, okay, then this has to be slow zero in order for me to continue this process.
Thank you.
So your quiz is sketching derivative graph, which we did at the beginning of class, optimization problem, which is all extreme value theorem, mean value theorem / rules. And the others are first derivative test, test for concavity, and second derivative test. So those are all the topics. Anything that you guys want to see? Yeah.
First derivative test to see if there's a relative maximum in the second derivative.
Yeah. So we can do two instances of that. Yeah, why don't we do it? Example. Okay, try this one here. Number 4. Find. Well, actually, number 4. Don't worry about the increase decrease. Just find relative max, relative min. And for number 4, you're going to go through second derivative test. So let's try second derivative test for number 4. Yeah, you'll set f prime equal to 0, find your critical points. And then rather than creating the sign line, you're taking those critical points from f prime and plugging them into the second derivative function.
It's actually looking for what's in it. You're not upstairs. Right. Hey, do you want to spice your stuff and probably push over? Yeah. All right.
So students struggle with this. That 18 positive number, students want to say max. At negative 18, students want to say min, right? We associate positive with high, negative with low. So, but we have to think about concavity here. This is an abstract number. The fact that it's positive is what's important. Positive means concave up. The only relative extremum we see on the concave up graph is relative min.
The first derivative test finds relative min max.
At using the sign lines here. So yeah, so if you wanted to go through first derivative test, you would do this. And then you would confirm, and then you would, say that -2 is a relative max and 1 is a relative min using the slope sign lines. But second derivative test, you use the same candidates, but you go through a different process. You put it into the second derivative function and look at the result of the second derivative to determine if that point is a min or a max.
Okay, and then we can use second derivative test to tell us if it's concave up or down.
No, that's test for concavity.
Okay,
Yeah, test for concavity would be where you set that equal to 0, find those critical points, and create your concavity sign lines.
how do you know it's concave up there?
Right here, because this is a positive value. So a positive second derivative means concave up.
Okay,
And concave up has this shape. And the graph with the concave up, the only place where the slope 0 that exists is going to be right at that point, which must be a relative min.
okay,
Because we already know that these are places where slope is 0. So if you're combining the fact that it's slope 0 and it's concave up, we can conclude we must be staring at a relative min.
so we use second derivative test, find relative min. But it also tells us if it's concave up or down.
We use it, no, yeah, so the term second derivative test is this process. But we do use a second derivative function to also tell us concavity if we go down the process of looking for critical points from F double prime. So if it's a separate problem, if the problem says find point of inflection, intervals of concave up and down, then you would actually set that equal to 0 and find those critical points from that dual prime. So if that's the problem, then you would say point of inflection is a -1/2. Here's my interval of concave down. Here's my interval of concave up.
Okay. And then our justification in the second derivative test is there's a relative minimum at x equals 1. Because,
F double prime of 1 is greater than 0. Therefore, concave up.
and do we also have to include that f prime of x equals 0?
No, I would say your process would demonstrate that knowledge.
Okay, thank you.
So this is first derivative test. This is second derivative test. This test for concavity. Okay, so in class, we're going to do that single sheet and then also finish up problems from the original, from your quiz review packet.
We have to memorize any formulas.
Just mean valley theorem. the steps for extreme value theorem. Your conditions. But no formulas, not really. Or surface area and volume, but remember surface area, you're building it, right? I don't want you to memorize it. I want you to build it. But yeah, I guess volume of a box, length times width times height. Yeah, that's it. Yeah, yeah. If you can make it past that first condition, the second one will just follow for the most part. But I'm not going to talk about the exceptions for that on this quiz. So yeah.